is infinite, in other words, infinite slope, okay? Or if we have a break in our graph, okay, our graph does something and then breaks off like this, if we have a jump. In any of these cases, our function is not going to be differentiable at that point. So at all these points here, our derivative doesn't exist. So keep that in mind if you ever have a graph that looks like any of these and you're trying to figure out, you know, what's slope tangent line there or what's the derivative there, it's not going to exist. And that just means that the limit, you cannot take that limit. The limit will not exist when you try and evaluate it. Now, we also have a theorem, though, that is somewhat related to this. It says if your function is differentiable, which means if you can take its derivative, if that limit exists, if differentiable, then f must be continuous. And remember, continuous means that you can draw it without picking up your pencil. So be careful in the order in which this is stating things. It's basically saying is that if you have a slope of a tangent line on the graph somewhere, then that graph has to be continuous at that point. It is not the other way around. So a lot of people make mistakes and they think that this theorem can be read from right to left. So let me give you an example. This cusp, right? That's a continuous function because you can draw it without picking up your pencil. However, at this point, we're not differentiable. So just because you're continuous does not mean that you have to be differentiable. But if you're differentiable everywhere, so let's say you have a graph that looks like this, everywhere you go, you have a nice derivative, it's defined, slope of tangent line is defined everywhere. If it's differentiable everywhere, then it must be continuous there. So that's the theorem. Keep it in mind. Now, since we have this idea that you can start with a function, and from that function you can take its derivative and create a new function, well, what stops us from doing another derivative of that function? Well, we can, and it's called the second derivative, and we use a double prime mark there, double prime. And we could also go 3. So you could take the derivative of that, and you can keep going forever. So let's see, what would come next? 4? Well, we kind of run out of prime marks, so what we do instead, okay, what we do instead of the primes is we just write a little 4 in parentheses. And that lets everyone know that what we're doing is we're taking the derivative 4 times. And then we could do 5. And then, of course, you know, as many as you want, you could do n derivatives. So this notation here means you're taking the nth derivative. Now, do not confuse that. You know, do not confuse f with the little 5 there of x. Do not confuse that with this. These are totally different things. This means take the function f and take its derivative 5 times. The other one means take the function f and raise it to the 5th power. So this is like an exponent raising to the 5th. This one is 5th derivative. That's why we put it in parentheses. That way you can see it. So, all right. Now, using that notation, I want to go back to something that we had earlier. We said earlier that if you had a function that was distance versus time, position function, s of t, we said that the velocity was the derivative of s. So we have that. And we said that the acceleration was the derivative of the velocity. Well, if you're looking at the derivative of velocity, and velocity is a derivative of s, then you could really say acceleration is the second derivative of the position function. So all of these are kind of connected to each other. All right, start with the position function, take its derivative, you get its velocity. Take its second derivative, you get its acceleration. Now that was for linear motion, remember. All right. What we're going to do now is we're going to try and do a little practicing of sketching what derivative functions look like. So let's say we have a function. I'm going to make one up here. I'll draw it in red. let's say it does this. Let's say that it goes up, and then it goes across, and then it goes down, and then back up like that. All right. So this is f. What would its derivative look like? So I'm going to start with the easy points. Let's start at 0, and I'm going to do the derivative in red. If I go up at 0 and I look at the slope of the tangent line, the slope is 0. So what I can say is that the derivative of f at 0 is 0. Right? Now, what I need to do is I need to plot this like an ordered pair. At 0, I get 0. All right? And this is my derivative function that I'm about to graph. So I'm going to put a green dot here. At 0, I'm at 0. So now let's pick another point. Let's go out here, let's say about right there. If I go up, what's the slope of tangent line there? Well, let me just call this point, I'll just say it's 1, just so it's easy. I know the derivative at 1 was 0. That means I can look at that as an ordered pair. Again, at 1, I should be 0. That's what the derivative looks like. So at 1, I should be at 0. In fact, if I would have picked any points in here and would have looked at the slope of the tangent line up here at top, it would have been 0, which means that my function, my green one, my derivative, should be 0 all along here. And it should stay 0 all the way until I get to here. All right, so it should stay 0 all the way to there. Now, once I get past that, well, you know what, let's go back to the left. And notice that if I pick any of these points, or actually any of these points and look up, all my tangent lines are 0. So I would have 0 for my derivative function all the way until I get to here. Now, let's pick something over here. Let's say we pick this point. We come up here. It has a slope. I'm not sure what it is, but it's some positive number, which means that, and since I can't tell what that slope is, it looks like it's about 1. Let's just say I go up 1 here. That's what my derivative looks like there. And if I go to this point here and go up, my slope is also 1. So it's like that. If I go here, my slope up here is also 1. So it looks like that. And it looks like that all the way over here until, well, the graph ends, so I'm just going to stop it there. So it looks like that. Now, on the other side, come pick a point, come up here, take a slope. Looks like it's -1. So what I'm going to do is go down 1, plot -1. If I pick a point here, come up here, slope a tangent line, that looks like it's about -1 also. And then over here, it looks about -1. So it looks like it stays -1 all the way over here until I get to here. Now what happens is, as I get closer and closer to this bottom point, it looks like that slope's becoming less steep, which means that it's less negative. So what happens is this down here starts to come up until I get to this point right here where it's actually bottomed out, and here my slope is 0, which means that my green graph needs to cross through 0. And then as I move to the right, anywhere over here, my slopes are starting to become positive, which means my green graph needs to be positive. And it looks like they're starting to get steeper and steeper, so bigger and bigger values. So I hope this all makes sense, but the derivative here, the derivative is graphed in green. So you can see that starting with the original function, we know that we can take its derivative and create a new function. That new function has a graph, and this is the graph of it. So the challenge will be for you to try some of your homework problems to start with the picture and just look at it, what its derivative would look like. Now there's some things happening here. We're going to leave these open circles here so that we know nothing's going on at those points. There's just jumps in the graph. All right, getting to some problems here. Let's take a look at more computational stuff. And I think right now I'm going to take a quick little break. Okay, back to work here. So we're going to do a couple of examples now that we've got most of that graphical stuff out of the way. Let's take a look at a problem like this. F of x equals x squared minus 1 over 2x minus 3. All right, we are tasked in this problem finding the derivative. All right, so we've done this before. The only difference here is that we have an x there instead of an a. So we're going to use the definition that the derivative of a function f at x is equal to limit as h approaches 0 of f of x plus h minus f of x all over h. So as before, what we did was we plugged, earlier we plugged a plus h in. Now what we're going to be doing is plugging in x plus h. So we're going to be replacing x with x plus h. We have to be very careful when we do this because a lot of people kind of just like to throw an h out here at the end, say, oh, that's what it means to plug in x plus h. But remember, the entire x here gets replaced with this instead. So I'm going to write this out. I'm going to actually do this like scratch work. What is f of x plus h in this problem? Well, it's x squared, but I'm going to be doing x plus h instead. Then minus 1 all over, and then the bottom is 2 times x, but I'm going to replace that x with x plus h, then minus 3. All right, and now I'm going to have to figure out what, minus f of x is. Well, f of x, of course, is just the function itself. I don't have to do anything to it. So I'm just writing things down right now. I'm not actually putting it all together. And then I'm going to divide that all by h. So here we go. The derivative of f at x is equal to the limit as h approaches 0 of this ugly thing, x plus h squared minus 1 over 2 times the quantity x plus h minus 3. Then subtract from that f of x, which is x squared minus 1 over, over 2x minus 3. Then divide all of this by h. Now, if you let h go to 0 right now, you're going to get 0 over 0, which means that we have to do some algebra before we can do any of this. So this will equal, all right, limit h goes to 0. All right, the numerator is a complex fraction. So we've already seen with complex fractions, what we need to do is we need to insert things top and bottom here, so that we get common denominators. Well, the common denominator I'm going to need is going to be this guy next to this guy. So I'll have to put this one here and here, and I'll have to put, let me use this one here and here. And that's what I'm going to write on my next line. All right, so big mess. I have my 2x minus 3 on the top and bottom. 2x minus 3 times, now the top left here was that x plus h squared minus 1 over, now the bottom was 2 times x plus h minus 3. And then we had minus, then I had my x squared minus 1, my 2x minus 3. And now I'm going to come in here and put that other denominator, which was this one. I'm going to put that right here and here. So I'm going to put 2x plus h minus 3 over 2x plus h minus 3. Now, all of this is divided by h. All right, fun stuff, right? So what we need to do now is multiply this here, put all that together, and then multiply this here. So in this multiplication, it might be worth it for us to first try and simplify what this is before we multiply that through. So let me go ahead and write out the limit. H approaches 0. It's going to be a lot of writing here. 2x minus 3. Then we have all that stuff becomes x squared plus 2xh plus h squared, and then minus 1. So I expanded this out, and then I had the minus 1 there. Or I expanded it out, multiplied it times itself, collected like terms. And then that's all over my common denominator, which was the 2x minus 3 times the 2 times x plus h minus 3. Then minus, over here, I had